everyone. So on behalf of IEEE W5OT 2020, we welcome everyone. We welcome the panel members. We welcome the attendees and participants for the last day of IEEE W5OT tutorial week. So today is August 7th, 2020. So today we are having the fifth presentation, and the tutorial topic is understanding IoT security risks and resilience from networks to supply chain. So the presentation will be given by Junaid Farouk. He recently joined the University of Michigan as a faculty member, and he's the co-presenter is Quinayan Zhu from New York University, USA. So welcome, Junaid. So you can introduce yourself and your guide and start the session. Good luck.
Um, Thank you, Bella. Can you shift the control to me? Perfect. Right.
Yes.
So thank you so much, Bella, for the introduction. And thank you for inviting me to present at the IEEE World Forum. I recently graduated from the New York University and joined the University of Michigan at Dearborn. And this work is jointly with my advisor, Professor Quinayan Zhu at NYU. So today's session is about IoT security, and we are all aware that security of the Internet of Things is a critical concern. But at the same time, it is a very, very broad topic. So there is no simple fix for it. We can go arbitrarily to any level of detail when it comes to security. So in this talk, what I'm focusing on is really high level or system level security that involves a large number of devices, because that's where the security really matters and it's the most crucial. So what you will see during the course of the next 2 hours or so is how security and resilience can be embedded into networks and even the supply chains of those networks. So let's get started. Okay, let's see how, I guess slides are not moving.
If you look on the left side of your screen, you can see where it says 01.
Yeah, but it doesn't seem to move. I have the control.
Yeah.
Apparently it seems not to move. Maybe I can share the file again, perhaps.
Okay.
So okay, do you have the file now?
No, I don't see it.
Okay, just 1 second. It should be there now.
Not yet.
Oh, do you see it?
No.
It just showed up, Karen.
Yeah, it's just going to take a minute or less. It's still loading here. So anyway, the whole idea here is that over the last decade, we have seen a shift from a paradigm that was referred to as the Internet of Computers that we've been all very familiar with. But what we're transitioning now today is something called the Internet of Things, where everything is getting connected together, including very ordinary devices that are becoming smarter and getting connected to this entire network. And as you'll see as the slides come up, that basically security of the computers has been very well studied in the past, and we know what the threats in computers are, how they can be attacked, how we can make our networks secure. But unfortunately, when we talk about the Internet of Things, security aspect is not very well understood, and it's still in its infancy. So we really need to stress on how we can make the Internet of Things secure. And the troubling factor is that the things are much more vulnerable to threats than computers were ever. So that's something we need to really look into. And hopefully this will be there in a second. Are they there?
No. Yeah, we got it.
Yes.
We got it.
Yeah,
Okay.
now they're up.
So,
And they're working. Wonderful.
So this is an overview of how the next 2 hours are going to look like. It's going to be in two main sections. As I said before, we are going to talk about networks of comprising of the Internet of Things, and then their supply chains. So the first section is going to talk about mainly on how networks can be secured from particularly coordinated or high-level attacks. We'll have a small break in the middle, and then after that, we are going to focus on how we can mitigate supply chain risk in IoT sort of networks before we conclude. So let's get started. I think we are all aware that the Internet of Things is really revolutionizing how electronic systems have been operating over the years, and we're having new emerging paradigms such as smart homes, smart factories, smart buildings, even smart cities. And the benefits are really clear. We have a lot of efficiency, a lot of productivity enhancements that the IoT is bringing, and that's what's leading to this massive adoption in all industry verticals. But unfortunately, on the flip side, these automated functionalities are not without their risks. So we really need to focus on this security aspect as well. Particularly, I would like to highlight these ordinary but yet very powerful IoT devices, which are these digital voice assistants. Apparently, they seem to be very ordinary, very low cost, and simple, relatively simple IoT devices. But over the years, they are becoming extremely powerful and computationally very capable. But they are not toy devices. In fact, they are able to interact with infrastructure systems, which can be critical. For example, they are interacting with electronic door locks. They are controlling thermostats in buildings. They are even connected to these smoke alarms or other sort of sensors, which can in fact trigger emergency responders and so on and so forth. So this is a very alarming sort of situation where very ordinary, simple IoT sort of devices can actually interact with the physical world and then cause a lot of damage if they are not properly secured or left at the hands of attackers. The reason why these systems are too insecure is due to the following. First of all, they are designed to be low cost. So a lot of emphasis has not been paid on their security. Then, because of this competitive environment in the market, the product development life cycle is extremely fast. And oftentimes the security is an afterthought. It's not part of this development cycle that they go through. Another important vulnerability point is the fact that these devices are inherently designed to communicate with each other. But when they do, it also opens doors for malicious activity, because each of these devices can become an entry point for attackers to infiltrate the system and then cause damage. And finally, I think this whole ecosystem right now is quite under-regulated. And what that means is undergraduate students can pick up off-the-shelf hardware and program them to interact with critical systems such as HVACs, fire safety systems, and electronic door locks, and so on, and then become part of this whole ecosystem, and may program it in a way that may not be, that may cause some unintentional functionality. So now when we want to talk about security, we need to think about what can go wrong in these systems. You might have seen these sort of notices when you go to public transportation spaces that do not leave your bags or luggage unattended. And when you see this sort of messages, there is some underlying threat model, because there's an apprehension that these luggages might be taken away or altered in some way. So the precaution here is, do not leave them unattended. So now when we talk about an IoT sort of network, again, we need to think about what can go wrong, and that can help us devise some security strategy to protect them. Okay, so in IoT networks, there can be several different consequences, and I perhaps give you two examples here. So first example, consider there is a community that deploys these thermostats, which are smart, and imagine they are deployed at a large scale in every household. And think about the case where every thermostat requests a change in temperature. When they do it together, there can be a massive surge in the power requirements or the power demand. And this relatively simple, but it's a legitimate operation, may actually cause a grid breakdown, because the grid may not be prepared for such a massive demand. So just by manipulating these devices may cause a breakdown in the power grid, which is a huge sort of an attack. Another example can be, for instance, think about these smoke detectors, these smart smoke detectors. Imagine, again, they are deployed at a large scale. Every household has a smart detector. And imagine all of them request for emergency situation at the same time. And if that happens, the public emergency responders may get overloaded with fake or superfluous requests, and that may sabotage this whole emergency response. So the point I want to highlight here is, just because of even legitimate operation at the IoT layer or the IoT ecosystem may cause attack on the physical systems. So that's the motivation behind the security of the IoT. Another example I want to give here is not really an attack that happened, but may happen in the future. So this is a picture of the Manhattan blackout in New York last summer. It was not a consequence of an attack here, but my whole point is that all these devices, which are increasingly starting to get deployed in metropolitan areas, may easily cause such a consequence. And if things happen in large metropolis like the New York City, I think the consequences can be humongous. So we really need to pay a lot of attention at the security aspect, and particularly I would stress that the large scale and coordinated attacks are the most um, critical ones that we should really focus on. Again, we can go into arbitrarily detail of device level security, but this talk is going to focus mainly on higher level and system level security policies and decisions. So now let's map out the threat landscape in the IoT. Whenever we talk about threats, um, there are three categories that we can put them into. The first one is the known knowns. That means there are threats that we are aware of and we understand them. And the classic example is the denial of service attacks. They've been here for a long time and we know how to deal with them. We know that they exist and it can be taken care of. But then there are known unknowns. For example, we know there are certain attacks that are there, but we don't know how to deal with them. And finally, there's unknown unknowns. There are attacks which may happen in the future, and we are not even aware of them, and we don't understand them. So for the sake of this talk here, let's not go too far. I'm going to focus mainly on the known unknowns that we are aware of, but we do not know how to handle. So let's try to be a bit more cautious here and try to prevent against them. A classic example that I want to give for these sort of attacks is the Mirai. Mirai is a botnet that happened in botnet attack that happened in 2016. And for those who do not know what a botnet is, it's a group of bots or malware-controlled devices that come together and launch a collective attack. So these small bots in individual devices, they collude together, they come together and do some sort of an activity. In the case of Mirai, it was just generating superfluous traffic that actually took down large websites like Twitter, Netflix, CNN, Guardian, etc. So the important thing here is that it was launched by IoT devices. And what the attacker did was they exploited default login and password. So you see, oftentimes when people install IoT devices off the shelf, they do not change their login and passwords that came from the factory. So some attacker may in the future exploit this vulnerability and get hold and control of a large number of devices. And when you have control of such large population of network connected systems, you can actually cause a lot of damage. So there could be other known unknowns, and we're hearing a lot about things like advanced persistent threats, which are stealthier, they are more prolonged and targeted. So we don't understand them much, but we know they are part of this threat landscape. Similarly, there may be backdoor channels in devices that are embedded by supply chain actors to attack the system at a later point in time. There are also other type of botnets which are prevalent right now. For example, there's one called IoTroop or Reaper that we are aware of is spreading over devices, but the attack has not happened yet. So the question here is, how do we tackle those known unknowns? If I go back to the luggage example that I gave earlier, one possibility is we don't leave the devices or network unattended. That means we have to continuously keep a check on devices to make sure that they are not in a compromised or controlled state. Again, this is a very hard thing to do, but at different levels of abstractions, there are ways we can make sure devices are protected. And I'm not going to go into the details, but at a very system level, if we understand the level of compromise of the devices, we can actually make decisions that can ensure the security of the system. So I'm going to take an example of a botnet to help explain how system level security can be obtained. And in the coming slides, I'm going to talk about mathematical models and theoretical frameworks that can allow us to make decisions to model how these risks propagate, how threats can be measured, and then how we can control them. So if we talk about botnets, which are stealthy, that means a malware might be propagating into the network without us knowing its propagation. So that means it's a stealthy sort of a malware or an attack. The question is, how do we prevent against that? Well, again, one way could be to patch devices, and to patch means to bring them to an uncompromised situation. It's a very generic term that I'm using here, but it could be in many different forms. For example, you could update the firmware of devices. You could power cycle them. You could patch them with latest updates. And there are many things that can be done. Again, this is a detail that is beyond the scope of this talk today. But the important concept here is devices can be protected using different levels of security measures. But the question again would be, even if we were to patch devices, how often should we patch them or protect them? Because devices have functionalities that they have to perform, so we cannot keep focusing only on the security aspect. They have to have these performance functionalities that should be fulfilled. But hopefully, if we can manage this security risk using the patching aspect, we can lower the risk of large-scale coordinated attacks, and that's the hope of this talk today. So when we look at designing such sort of mechanisms that can achieve this level of security, I think we are looking at three different things. First is the system should be secure by design, meaning that we want to embed security features into the design of the system. We don't want security to be an add-on. It should be built in instead of being bolt on. So you will see as we progress through this presentation how the mechanism itself can be made in a way that that has those security features in it. The second thing is being scalable. Again, because we are talking about large-scale, massive networks, whatever we design should be scalable, should be applicable to large population of networks. And finally, I think the important thing is manageability. And to be manageable, any policy or any framework that we develop should be implementable in a distributed manner. And what that means is you should not have a constraint on the policy to have a certain structure, but it should be implementable for every device independently of other devices. So that's kind of the thinking process that goes through when we talk about designing these security mechanisms. So this was all introductory stuff that I wanted to talk about before we really go into how we can model these things and how actual mechanisms can be developed. I'm now going to introduce some mathematical modeling that can be done, and then using some theoretical frameworks, how we can measure the risk propagation or the threat propagation through networks, and finally, how we can design some policies that help prevent those. So, because we are talking about IoT devices, and these devices are wireless communication devices, they can be located anywhere. So there's a lot of randomness in their locations. So to model them, what we make use of is something called a point process. It's a stochastic process that models the location of these points in space. There are many different types of processes that can be used, but for the sake of simplicity and for generality, I'm introducing here the Poisson point process with some intensity. It's a parametric model. So assume lambda is the density of this point process in space. It's extending all the way from in all directions in space. So imagine every device has wireless communication capabilities and is also running some computational processes. So any device may have regular processes running on it, or it may also have some malware process running in the background, which makes it a bot device. So these devices are free to communicate between each other. Whichever device is in the vicinity, they can actually connect with them. So this figure here shows you how it's just one instance of the process where some devices are within the wireless neighborhood of each other, so they're able to communicate at least some information with them. And their wireless interface may also be used by some malicious actors to basically propagate this malware through the wireless interface. So a bit of notations before we move on. I'm using a wireless communication range of R meters. And as I said, within a wireless neighborhood of R meters, devices can actually connect to each other. So, so the degree of the device is very important. So again, looking back here, each device can connect to a certain set of devices in its neighborhood, and their number is called the degree. So for example, here the device in the center that we have has a degree 3 because it can reach 3 other devices through its wireless interface. And because our chosen model is a very well-known stochastic process, it has known statistics. For example, we know what the degree distribution is in terms of the system parameters. So for instance, in this model, we know that the degree is a Poisson random variable, and it depends on the density lambda and the communication range R. So these are just modeling fundamentals here that helps set up this ecosystem for understanding how risks may propagate over these networks, and then how we can exert some control over them. So just to show you how these sort of models may be valid or useful in real life, what I did was I took the data of New York City hotspot locations, wireless hotspots that are deployed in many different parts of Manhattan, and I actually considered these as IoT devices with some wireless communication range of 140 meters, which is typical for Wi-Fi sort of systems. And then I analyze how their neighborhood profile looks like. And what the result shows is it can be reasonably approximated by a Poisson distribution with some density. So the whole point here is that models of the sort of Poisson point processes are actually useful. They may not fit all sort of scenarios, but from a very macroscopic level, you can actually use them to model many different scenarios, and these are tractable, so they offer a lot of they offer this flexibility of tractability and nice results that can help understand how system parameters relate to the solutions. So let's move forward. Once we have this networks model set up, I think the next part is what sort of threats we are considering. So I'm thinking about a bot master here, who is kind of the author of the malware which may spread in the network. So I'm assuming there's some P proportion of the network that may be vulnerable to infiltration of the malware, because all devices may not have vulnerabilities. And vulnerabilities can be as simple as having default password. So it's just a parameter here to help capture these sort of problems or security issues, flaws in the devices. Now the model here is that individual devices try to propagate or self-replicate the malware within their wireless neighborhood. So any device which has already been captured by a bot is going to attempt to replicate the same malware within its neighborhood. And hopefully once this reaches a large part of the network, then an attack might be triggered, and that is going to cause a large scale attack. So I'm assuming there's some propagation rate of the malware. So any process which is malware infected, it's going to propagate itself with some rate gamma B in its neighborhood, and it's going to send out commands as well at the rate of gamma C. And hopefully, if some administrator is patching these devices or is returning them to an uncompromised state, it can get rid of this malware process. And finally, from a realistic point of view, we need to take into account the wireless links between these devices, because they have this wireless medium. So there's some probability that the messages might be lost. So we have this parameter row that captures what probability the messages become successful. So now we're going to talk about how this malware transfers and evolves over the network devices. So we have talked about the network model, which is a Poisson point process, and we have talked about attacker capabilities. Now we want to talk about how this malware propagates in the network. And a very useful mathematical framework here is the one of epidemiology. So that means we can get inspired by how epidemics spread in human populations, just like the coronavirus. But we want to study those over networks, because networks are different than humans. So this is a very useful mathematical model that helps capture how viruses or malware may propagate over devices, but through a wireless interface. So the figure on the left here shows you the situation where the devices are randomly located in space. The green dots show the device is uncompromised, and the red dots tell us that they're compromised. And within the wireless neighborhood, any device can actually transmit the virus to another device and make it infected. But there's a catch here. So any device depends on its wireless neighborhood, but its neighborhood depends on itself. So if you see that there's this reversible link between devices, so just like I can get you infected with the coronavirus, you can also get me infected. So there is this reciprocation sitting somewhere, which is a very beautiful mathematical concept, and we are going to deal with it in evaluating how the eventual spread of this malware can be in large networks. So to model this this sort of behavior, we are going to use a Markov model, and with the three states. The first state is the uncompromised state, which is referred to here as the B tilde. And then any uncompromised device may become a compromised device, but may not be informed with control commands. So we call it this BI tilde. That means it's a bot, but it's not informed with control commands. And the last state is being a bot and being informed of the control commands. So you actually hop from one state to the other, and eventually, if you are patched, you might return back to the same state. And this patching process here is shown with this probability mu. Mu is the rate at which devices are being patched. And notice all these states are dependent on this subscript k. That means we are depending on the degree. So any device actually behaves differently depending on how connected it is. So this model that I'm trying to explain to you here depends on individual network nodes or devices. So if a device is not connected at all, it may never enter this process. But on the other hand, if a device is connected to a lot of other network devices, it may be very vulnerable to malware infiltration and attacks. So this Markov model helps explain how the malware propagates over the network and how it moves over time. So it's really a dynamical system that is forming up here on top of the physical network. So recall again, we had a physical network that comes from the Poisson point process, and there is a model that explains the attacker capabilities and behavior. And using that assumptions, we build a dynamical system over this. So, which is defined by this Markov transitions. So using this diagram, we can simply go ahead and write the dynamical system, which is coming up in the next slides. But before that, I might take a minute to explain these probabilities. So any device which is in B tilde can actually become a BI tilde with some probability k times sigma 1, where k is the degree and sigma is the probability that you are actually connected. It's the probability of being connected to a bot device or an infected other neighbor. So similarly, once you are in BI tilde, you can then go further to this BI. And these probabilities actually depend on many factors, like how vulnerable the device is, which is the factor P, the wireless channel, which is the factor rho here, at what rate the bot or malware is being replicated, which is the factor gamma B here, and so on. So there are a bunch of different factors that influence what rate this malware progresses over the network. And that's the beauty of this model, that it's modular and it depends on physical parameters. So using this Markov diagram that I showed you, we can actually write a dynamical system here that shows how the population of those type of devices evolves over time. So these differential equations tell us at what rate over time the bot population evolves and how it decreases and how the system evolves and is interlinked with each other. And because we know that all these populations add up to 1, that means the entire network, we can actually further reduce this system of equations to just 2, and that's where we want to analyze them further and work with them to understand what the equilibrium looks like. So the entire idea here is to understand what the eventual state of the network will be. How many devices are going to be infected if such a process is running on it? How many devices would be free of any malware? So these are governing mathematical equations that help us measure these very important quantities. There's going to be a lot of challenges solving these sort of systems. I might not go into a lot of details, but it's there in the slides, and I'll briefly go over it. So in order to solve this sort of dynamical systems for equilibrium, we can actually end up in this self-consistent system that needs to be solved consistently. So we actually end up in a kind of interlinked system, intertwined. So there's this equations in b's, which depends on some thetas, but then there are equations in thetas, which depends on the b's. So these has to be solved self-consistently, and it's not easy because the degree profile of the network is complex and the system is very hard to solve. So we may need to end up in using some approximations to actually simplify the system and help us obtain some tractable results. And this has been done in one of my recent works, and I'm not going to go through the proofs here, but some main results I am going to talk about are the equilibrium. So the equilibrium can actually be characterized using some approximations again in some tractable format here. But these may not be smooth. For example, here it depends on some min function and a max function. So actually we can approximate them further using some smooth approximations, some smooth functions that convert them into differentiable results. So using them, eventually there are a couple of things that we can obtain here. First is some fundamental limits. So using this model, we see that there's some maximum limit sitting on parameters like the patching rate. So the mu here is a patching, and we figure out that there's the maximum rate of patching beyond which there is no benefit. And it depends on how connected the device is, the wireless link probability, the vulnerabilities in devices, and the propagation rate. So this result is quite elegant because it helps understand what is the maximum or what is the limits in terms of securing the network. What is the maximum security you should provide beyond which there is no benefit. Instead, it's just an overhead that you do. And we will see once we get to the results how this comes into picture. So finally, after some manipulations, which I'm not going to go through, these are the final equilibrium results. They look very scary and messy, but they are really smooth, differentiable results of equilibrium of the malware propagation. That means it tells us, using the network parameters, where the eventual system state will be, how many devices are going to be compromised all the time, and how many wouldn't be. So these are really elegant results, but may look a little bit complicated. And in the following slide, we are going to see how we can make use of them. So now we have modeled the system. We have talked about the attacker. We have model the propagation of this malware over the networks. And these are really random spatial networks. So now the problem here is, how do we defend the network? We have seen where the attacker can eventually go, but how do we protect it? For this, we need to come up with an optimization problem that focuses on developing a patching schedule, which has a minimum cost. The trade-off here is, if you patch too much, you are going to disrupt the network from regular activities. But on the other hand, if you patch too less, then there's higher risk of coordinated attacks. So there has to be some balance that needs to be achieved. And using these theoretical constructs, we have actually come up with a very elegant method and model that defines at what rate these patches should be applied. So one example of a optimization problem is the following that we have set up. There could be many others. We want to try to minimize the cost of patching, and the cost of patching is a very generic function of the patching rate. So we want to minimize the approximate cost of patching, subject to the fact that the total number of, or the expected number of compromised device does not reach a certain threshold. And these are some arbitrary numbers highlighted in blue here. So tau b tilde and tau bi are some numbers that can be set by the designer. And these are figures that restrict how many devices can be compromised, or what proportion of devices can be compromised, and then what proportion can be compromised as well as informed with control commands. So there are these two main constraints that we can put on the system, and then design our patching rate for every degree device. So for every degree k, we are going to have some number that tells you how to patch that device and at what rate. This is the result here. So on the x-axis, we have the degree of the device, and then on the y-axis, we have the optimal patching rate. So for every degree device, we, based on different thresholds, the taus, we get some optimal patching rate. And there's this dotted line here that shows you the maximum possible patching rate. So as I showed you earlier on the fundamental limits results, that there is a theoretical upper limit that we have for every degree device. And our results confirm that no patching result goes above that. Just to mention, these orange lines in the backdrop is actually the probability, or it's a Poisson distribution. So as we said, the degree of devices is a random variable with a Poisson distribution. So it has this probability density function. So you see there's a lot of devices with the average degree of around 10 devices, and then it rolls off on either side. So you see the devices that are more connected have a higher patching rates, and these rates, they saturate at the theoretical limit. So there's no point of doing anything beyond that. So I'm not sure if I can show a video here, but we can actually do a simulation where a random network is infiltrated with some malware, and then it spreads to its neighbors. And once the whole network is covered with malware, we can actually implement this policy and see how the network evolves. But I do have some screenshots here. So these blue dots shows network, randomly placed network devices, and the red dots here shows the ones that are compromised. And the three figures are for different thresholds. We have this tau b of 0.7, that means we are expecting that 70% of the network should be bot free. And then in the middle, we have 80%, then 90%. So as we see, these are the final configurations after we have implemented this patching policy. So even though the malware is still propagating, but because of this optimized patching, you see that we are able to reach these targets of 70, 80, and 90% from our theoretical modeling and from the system design. The policy has been designed in a way that even though these processes may still be running, hopefully if we are able to get rid of these malwares, we can ensure that overall a certain proportion of the network is going to be free. And that's where I say that we are going to avoid large-scale coordinated attacks. So even though, you know, malware may still remain in the network, but it's not going to coordinate with each other and cause some large-scale damage. The figure on the bottom shows here the evolution over time. So as I said in the beginning, all the devices over time get infected. So we start with 100% bot-free population, and then over time, the malware spreads throughout the population until every device has been compromised. So that means we'll go to 0. And somewhere in the middle, I implement the patching policy. So we quickly start recovering and then reach our threshold that has been defined in an average sense. So on average, we are able to achieve this target threshold that is set in the optimization framework. To show whether this sort of results can actually be applied in other type of networks, I also replicated the same result using New York City hotspot locations. So these are, again, 70, 80, and 90% threshold targets. So what I see here is that actually in these sort of cluttered scenarios, we can actually perform better because the device locations are not uncorrelated. So any malware may not get stuck in a loop. So basically, in essence, I think the Poisson point process is the worst case scenario because it's totally random. In real life, we have more correlations, and actually any policy using those sort of uncorrelated assumptions could actually perform better. So I'm going to conclude here with the first part of the talk. And in this part, I've given you an overview of the security challenges in IoT. I've given some examples on past attacks and some emerging threats. And then I have presented to you a theoretical standpoint on how we can prevent propagation of botnets in stealth mode. And we have actually integrated multiple theories from network science to population processes and then optimization, integrated them together to actually prevent large-scale attacks from happening, particularly with devices of an IoT sort. So I think I will, the key takeaway for you.
Good. So you're going to take a 5-minute break right now?
Just give me 1 minute and I'll give you a break.
Super.
So the message that I want to give here is system level security is a very important concern. Recently, there was the security breach where a person used 99 phones in Berlin to trick Google Maps to think that there's a traffic jam. So my point here is that these small devices that we think are not that important may actually have a huge impact when we look at the macroscopic level. So the security is really going to be a huge concern, and it should be dealt carefully. So I'm going to take a break here, and people are welcome to have questions at this point.
Yeah. So what I'd like to do is actually encourage people to put questions into the Q&A box. And I think it's 11:55, so we will give it 5 minutes and start promptly at noon again. Okay?
Perfect.
Okay. And I think there was one question about the availability of the recordings and the material. You should all be getting an email early next week or over the weekend that'll actually have the links to all of the material and all of the recordings. Okay?
Mm-hmm.
And so I think for the time being...
Adam, we have a question.
Okay, go ahead.
There's a question from one of the attendees. The attendee's name is Onur Vosturk. So the attendee's query is it meaningful to take connectedness of infected nodes under consideration for the strength of a possible coordinated attack in designing the optimal scheduling policy? Can I repeat?
Okay. Yes. No. I see the question.
Okay.
Actually, this is a good question. So it's trying to separate the network into two different parts. One is the devices that are not infected, and then there's a network of devices that is infected. But so the idea here is the compromised devices should be connected with each other, right? To actually form a coordinated attack. But what we're doing here is we are using peer-to-peer communication. So even though the devices are not connected with each other, but they pass messages to their neighbors, and then that message gets propagated to the entire network. And actually, when they want to launch an attack, they can reach some consensus. So if you really want to study how attacks are launched, I think there's going to be another layer on top of this, which is the consensus layer. Because imagine once devices have been compromised, they need to reach a consensus in a distributed way when to launch an attack. So because this is a distributed system, there is no centralized controller, so connectedness is not taken into account. But if you really want to study this, I think consensus is the way. I think here's a follow-up question.
Yeah, we have one more question. So we are assumed that infected node messages can be routed over uninfected nodes.
Actually, no. This is not the assumption here. We are not basically studying the launch of the attack. But at this point, only a node that is a bot can transfer the commands. So if nodes around it are not bots, so the control command propagation is going to be slower. It's going to be much slower than the propagation of the malware itself. But again, we have not reached the attacker's mindset. It's a preventive mechanism that is being developed or proposed here.
Okay, Junaid, I'm Bharat speaking. I have a small query. What is this equilibrium? You have mentioned in your slides
Yes.
there is something called equilibrium, and how is this linked to the attacks?
Okay, so there's multiple processes going on in the network. So just take an example of one single network device. It may get infected with some malware, right? So let's say it caught a virus. But at the same time, there is somebody who is patching this device. He's returning it back to the original state. So the state is changing over time. And when you look at the entire network, you can think about how many devices are compromised and how many are uncompromised. And this is changing over time. See? because there's a process running that is increasing the number of compromised device, and then there's process running which is decreasing it. So the equilibrium is the eventual state. Let's say both of the parties start acting at the same time. Where are things going to settle down? I mean,
Okay.
is it going to go all the way to all of them compromised, or is it going to go somewhere to zero? But because they have both different parameters, we want to study, what is the middle ground where they settle down eventually. So that's the whole idea of measuring it and quantifying it. Because once we have this quantification, we can actually exert some control over it. We can optimize things and tweak the parameters.
So if it is taking more time to estimate the state of equilibrium, then how does the system evolve and work? Let us say that the system is taking more time to get in a state of equilibrium. Then how does this model takes care of?
Again, this is a very good question. In this framework, we are not looking at the time required to reach the equilibrium. We are only looking at the equilibrium state. If you want to look at the time, I think we need to look at the eigenvalues of this dynamical system, and then try to place them in a way that system reaches the equilibrium quickly or slowly or whatever is desired. But again, that is the next level. It's not going to be simple.
Yeah.
So at this point, I am just looking at a long-term thing.
Thank you.
Right.
Yeah. Thank you.
Sure.
So should we have a break? We have only 2 questions from same person, and if you want, you can take break. And in case we have more questions, we can add these questions in the next session.
Yeah, sure.
Because we have only 2. Adam, is it okay?
Yeah, that's fine. Really up to you whether you want to take a few minutes or you want to restart.
Just 1 or 2 minutes, I think.
Okay. So we'll take a little bit of a break, okay?
Sure.
You have mentioned the slide in a 10 minutes break slide.
Oh, yeah. Yeah,
That's good. Yeah.
Let's get back at 12:05.
Yeah,
right?
yeah. 2 minutes break.
Give me a second as well.
Good.
Yeah. So I think, Junaid, at this point, we're almost at 5 after the hour. Why don't we just get going again, okay?
Okay, perfect. So welcome back, everybody. We're going to the second part of the talk here, and this is going to be related to the supply chain of the IoT networks. In general, supply chain is critical across all industry verticals, and be it food or manufacturing or transportation. We have seen under the current coronavirus that there have been shortages in supply of personal protective equipment like masks and sanitizers. So the healthcare industry has had a very difficult time. So particularly for ICT systems, let's just, yeah, so it's also important for the ICT systems such as the Internet of Things, because it's an enabling technology that is used to secure the supply chain of many different industries. For example, stores and warehouses, they use IoT technology to actually secure their supply chains. They have different sensors and actuators that help track equipment. Similarly, there are fleets of trucks that are tracked and monitored in real time. So paradoxically, the supply chain of the IoT is insecure itself, even though it is helping secure a lot of other things. And this is because most IoT devices are produced by international vendors, which cannot be relied upon completely. But it is highly important that supply chain of modern strategic systems such as 5G and IoT is also made secure. So when we talk about the IoT ecosystem, it is not a standalone system, I believe, like other traditional computing devices. In fact, it is an ecosystem that comprises of an integration of many different systems together. So if we consider a single IoT device, it can actually be a sensor or it can be an actuator. And the device may have some software or firmware installed on it. Then using this firmware, it connects to some wireless access points such as routers and hubs to reach the core networks using gateways and intermediate networks. And then once it reaches the internet layer, it connects to the cloud server that hosts some applications. And these applications can be operated or controlled by smartphones and smartwatches, and even voice assistants, as I mentioned in the earlier part of the talk. So, but the thing is, it is just one device that I'm talking about here. We have many, many different devices that are interconnected in the entire complex ecosystem. And each of these components that I've talked about is manufactured, owned, or controlled by a different entity. So from a high level, if we look at the IoT network, it can be seen as an interconnection of different devices. And I show here that each device may have its own supply chain that we do not see at the forefront. And what we also do not see is that these supply chains may or may not be linked to each other. So there may be hidden linkages between the supply chain actors that are not visible, but may pose as a threat when we think about malicious entities in the supply chain. So an even bigger picture, if you will, is when these networks get connected to physical infrastructure. So we know that IoT devices are deployed on physical infrastructure to make them smart. And these infrastructures may also have some interdependencies. For example, transportation networks may actually depend on electricity networks and so on. So if we think about the supply chain with these underlying connections, it is really a complex web of supply chain actors from a risk perspective. So as we talk about risk, I think risk enters this ecosystem from three main sources. The first one is the traditional system reliability risk that's always there. and it involves some failures, some malfunctions. Then there is this cyber risk that involves events such as malware, phishing, or other type of attacks such as denial of service, man-in-the-middle attacks, and so on and so forth. And the third source of risk is the supply chain itself. So the attacks from the supply chain can be either intentional. For example, some vendor may embed backdoor channels in the devices, but it could also be inherent due to the fact that we rely on just one or only a few suppliers. So this thing could actually create some supply uncertainty, and it may cause another risk to the system. So before I go into details and talking more about the supply chain aspects, let me just give you an overview of what I've said up till now. So the first thing is the IoT is becoming ubiquitous. It is massively being adopted in critical infrastructure systems. And the cyber-physical integration that is happening due to this adoption is opening doors for malicious activity. So in effect, the IoT is becoming a gateway for attacks on critical infrastructure. So we need to pay a lot of attention towards the security and resilience of the supply chain for IoT. The hypothesis that we have here is that the interconnection of devices is resulting in a complex web of suppliers, manufacturers, and even service providers that are entangled with each other in a very complex manner. So cyber-physical risk analysis helps to uncover this web of suppliers and allows us to measure how intense these threats are and how much they impact the critical infrastructure. And eventually it leads to making or helping us make some risk-informed decisions when we are buying these devices, when we are deploying them, and when we are upgrading them. So there's a lot of different processes that go when we talk about how to measure these risks and then how to control them and to avert them. But there are a bunch of challenges here. The first one is the logistical challenges. So, for example, how do we know which suppliers to trust? This is a hard problem, and there is no centralized disclosure of supplier-induced attacks. And also, supplier linkages are oftentimes hidden. We do not know the hierarchy of the suppliers. Additionally, it keeps changing over time. So there are mergers, there are takeovers that happen at the supply chain layer, which we often are not aware of. So it's a very dynamic problem. Then there are some technical challenges. Considering the fact that we are able to overcome these logistics, the risk analysis is itself very complex because of the nature of the system and the way it entangles with the traditional reliability analysis. So decision analytics in these systems is a non-trivial problem. So one way to approach this difficulty that I'm going to talk about is to develop a system which may have 3 different components. We assume that the system may take as inputs the metadata of the supply chain and information on how the system is interconnected. And using this information, we connect or construct a map of supply chain actors involved. Once we have these sort of maps, we can actually try try to develop a risk assessment engine that does scoring of risks and the propagation of risk. And finally, using this analysis to make some decisions regarding the supply chain. And by the decisions, I mean where to buy, which supplier to connect with, which supplier device to connect with, which supplier device, and so on. So there are a lot of decisions organizations take when they procure, deploy stuff that relates to the supply chain. So there's a lot of decision making involved, which can be actually improved if all this can be measured and controlled. So, as I said, basically, this is the overall approach that is being followed. We want to identify, we want to categorize, and map what the threat ecosystem is, how what actors are involved, and how they connect with each other. Then we want to look at the system, how vulnerable the system is, how risks can propagate through the system, and this comes through the structure, the overall structural integrity of the system. And then the last part is the decision analytics that we can develop. So a critical component that I mentioned for risk analysis is the supplier trust. This has to be some magical quantity that that is populated over time and is, as in human interactions, trust is something that develops over time and from repeated interactions. So it can be measured in terms of a probability or a possibility that some vendor might create a hidden backdoor intentionally or unintentionally. It could also relate to the reliability of the supply in the future. So there's a lot of different ways we can look at trust. But essentially, I think it is a perceived character of the supplier. And it is beyond the scope of the talk today, how we can measure or we can analyze trust, but it has to be there. And I think it is there. It's just a matter of quantifying it and actually putting a number on it. So, but it's really crucial once we talk about risk and risk propagation, not only in the supply chain aspect, but in any risk analysis work. So, one way of looking at trust is in probabilistic terms. So, from a device perspective, I think each device has some stated specifications and some actual functionalities. And some of these stated functionalities might be missing in devices, while there might be sometimes extra hidden functionalities, which may be implemented as a backdoor or some other extramural channels. So the trust can be measured in terms of the discrepancy between stated functionalities and the actual functionalities. And then this forms a probability. And this, of course, would require some expert knowledge of the system, as well as some extensive testing and vulnerability assessment. A classic example here is of Huawei, where there is a lower trust because hidden functionalities have been allegedly found in some of the systems. So examples like these can be motivators to actually develop some calculus for trust and to measure it accurately. So the question now is, how do we model the supply chain risk? We've talked about trust, we've talked about quantities that are important, but the factors to consider are how we can integrate the suppliers into the security risk analysis. Security risks are being studied for a long time, and Traditionally, people use a lot of attack trees as a useful tool from reliability theory to analyze those risks. But how do we integrate supply chain components into those attack tree models? That is the interesting question here. And the next thing is how we quantify the undefined risk that comes as an augmentation of suppliers and the system itself. So there's two things. One is the supplier layer, and then there's the system itself, which may have vulnerabilities or risks inherently in them. So we want to compose them together and see how they come together and form the overall risk analysis. So before answering all of these questions, I would like to introduce the system model that I'm looking at and that is being used here. So in the model that I consider, there are two set of entities. One is the components of devices. It can be in an arbitrary detail where component may be a physical component or maybe a subcomponent of an actual component. So there are two entities, as I said. One is these components, and the other is the suppliers of these components. Of course, these components are linked together in a logical manner to obtain some desired functionality of the device. What I have here is a very simplistic system with only two components, but in case of actual IoT and networks, this can be arbitrarily large and interactions can be significantly complex. But a very toy example is being shown here to make the concept clear. So the model that I'm considering is based on logical representations, and these are in the form of and OR logics. And each component has some associated supplier, and as you are going to see later, these suppliers also belong to some sort of groups or may have linkages between them. So now, if we think of the supplier, its involvement can be found in two different places. Firstly, it directly impacts the components by altering its reliability. Because if a component is obtained from a certain supplier, it may have a different reliability just because of supplier induced trust. But there's another entry point. Suppliers also provide specifications that people use to do vulnerability research or use to construct the attack trees. So there's two places that the suppliers actually play a role. So an imperfect supplier would limit the accuracy of how the risk is being computed. So what is central to our analysis or framework is the measurement of risk. This is a really crucial element. And traditionally, the way people measure risk is from reliability theory. They would compute recursively the probability of failure and often exploit some minimal cut sets of a system graph that is being constructed. But as you know, the systems get larger and larger. This traditional strategy may not be a very feasible for computing the risk. So there's a need to go to some other metrics that give some understanding of the structure of the metrics. So we have not been able to use traditional approaches when we talk about IoT and the risk evaluation. So we had to resort to some other sort of metrics. And two of them I'm going to mention here is the improvement potential and the burn bomb importance measure. So the improvement potential is a metric that identifies the change in risk by using two extreme type of components. One is a perfect component and one is a totally unreliable component, and it computes the difference that it creates to the risk of the entire system. The second metric is the Birnbaum importance measure, and it captures how sensitive the risk is to individual components, to the reliability of individual components. And in our study, we believe it gives a more accurate picture of the hidden structure of the system. Because imagine if the IoT system with a massive number of devices is considered as a black box, evaluating the risk posed by one component is a very difficult task. So metrics like the Birnbaum importance measure may give you some structural hints, some idea of how certain components may be important or may impact the overall risk of the system. So once we have this, basically, if we form a risk mitigation problem, then the basic problem is essentially to minimize some system risk function subject to some constraints. So there are constraints on the overall budget because the components have some costs associated with them, along with their trust and reliability. And then, as I remarked earlier, there's difficulty in using the exact risk function because of the large scale of the systems. So we need to resort to some approximations. And again, the one that I will talk about is based on the Birnbaum importance measure. So let's see. Once we do this, basically it is the linear weighted mapping of the risks or the reliabilities of individual components that is used as an approximation for the actual risk. And in our study, when the systems are large, these approximations are actually very close to the original risk. So we have used these approximations to actually help us in optimizing or minimizing the risks in large systems. So the next thing is the bigger picture that we want to look at. So we need to understand how supplier gets involved into the risk. So we have developed some way of measuring risk of the system, but then we want to see how the suppliers get involved. So I'm going to consider here a very simple toy example where the system is composed of just two components, component 1 and component 2, which is referred to as C1 and C2 here. C1 can be obtained by supplier A, while C2 can be obtained from supplier B or C. And now notice that the supplier A and B are controlled by the same entity and is referred to as the uppercase A. So if you make the selection as shown by the red lines in the diagram on the right, then any attack from supplier group A is going to affect both components C1 and C2 because they have this common supplier group. So therefore, it's a more risky solution as compared to the one shown on the left, where the components are obtained from diverse suppliers. So any attack from one of the suppliers may not impact the entire system or the entire components. So the overall risk, when we overall or combined risk metric can therefore be developed to capture both these two risks. One is the general risk, that is because of the reliability or systemic or the functionality risks. But then there's a group risk that comes because of this supplier groups involved. And then we can use this in the optimization. So this is one of the ways. I'm not going to go into the details, but this is one way to measure the risk that is coming from these supplier groups. And then we have to augment these together with some parameter alpha. We weight them and add them together to actually form the total risk of the system. So it has two components. One is a general risk, and then the other is a group risk. So if I want to summarize this, our solution has three stages. So the first stage, we are approximating a risk function using some component importance measures. This helps in scaling the analysis to large and complex networks. Then what I introduced is an integrated metric to measure the systemic risk and supplier involvement. And these are based on the metrics that I talked about earlier. And finally, the supplier selection optimizer gives us a minimal risk set of component vendors. So each group owner and equipment vendor is assigned a trust value in the example that is going to be followed here. So I'm going to take an example to illustrate that the whole idea. So this is a case study, a very simple case study of an autonomous vehicle. This is a simplified diagram that shows how an autonomous vehicle components may be connected. It's a very simplified version, just to illustrate the idea here. And there are components such as radar, camera, GPS, LiDAR. They are logically interconnected in a way that indicates some operation. So these components may be obtained by different suppliers. So here is just a map of, it's just a glimpse of the supplier footprint that is involved here. And if you see, there are many different vendors that provide various components. For example, LiDARs are provided by many different suppliers, and radars are from different manufacturers, and there's vision and camera, and so on. So there's a lot of different components, and there's a lot of different choices that we have. And the decision maker's problem is to pick suppliers based on their trust and cost and other factors, so that overall, once the system is built, the combined risk is minimized. Again, this is a toy example here. In no way we are trying to impose this on actual systems, but for the sake of simulation, I am considering the case when each component in the autonomous vehicle can be obtained from three possible suppliers. So this is just a hypothetical hierarchy between the suppliers, where the group owners each control 5 vendors. And this scenario here is constructed as an example to test what we developed for our risk analysis and risk mitigation. So on the right side, you see the components, then their possible suppliers. So there are 3 for each. And then they are owned by different super suppliers, if you will. So that's kind of integrated system where we have components and suppliers and then their own suppliers. And remember, there's going to be a system coming after this because the components are also connected together. So if we analyze the risk that propagates to each component from the trust level of the suppliers, we can notice that some components may have a higher risk of failing. But on the contrary, their role may not be very significant. And this is shown by the use of metrics such as the improvement potential and the Birnbaum importance measure. And as we see in this result here, the component V2I has the highest risk but it does not have a very important role in the system reliability. So the point that I want to make here is that it's important that we make use of different metrics to truly understand how the supply chain risk is composed of and how we deal with it. So if we look at the overall picture of all this scenario that I've presented, I think this picture is going to sum it up. We are having a components which are, so there are components C1 to C7 which are interconnected to form some devices. And again, these devices may be interconnected into some complex, in some complex fashion to compose the system. So this lower part of the diagram here is the system composition. And that's where we label it as a downstream risk, because there are components and then the connections go downstream to eventually comprise the system risk. But there is something which is upstream as well. So each component can actually be obtained by some suppliers, and then those suppliers have some hierarchy beyond at the upper level. So there are these two risks that come together, and the whole the goal of this work is really to combine them together to form an assessment of systemic risk, and then try to minimize this risk by making decisions at the supply chain layer. I mean, obviously, we cannot change the individual components or their reliabilities, but if the decision is only at the supply chain layer, there are ways which we can use and try to avert the risk. So here are some of the results that I have. So we are using just a single group owner and a supplier involvement is minimized. So as we have higher budgets and more possibilities, more reliable components, we can observe that the optimizer that we've developed is able to diversify the selection of suppliers in such a way that the common group owner is avoided. So the optimization is able to diversify the supplier selection. So we have been able to reduce the supplier induced risk to almost zero. So if we see all these figures successively, as you have more and more budgets available, more and more choices, you are able to actually make better choices in terms of the risk, and eventually we are able to filter out any common and risky suppliers. For a more developed case, we have another set of simulation results where we consider the combined risk metric. And we see that while the group risk still goes to zero as we have more resources available, but the general risk may still stay because of the reliability issues on individual components. And as we increase the priority of supplier involvement factor, which is this alpha factor here, there's a more aggressive reduction in the overall risk as well as the general risk. So, and the last part that I also investigate is how this alpha comes into the picture and how it plays a role. It's clear that there's a critical priority factor beyond which any emphasis paid on diversifying selection of suppliers does not work. So eventually it is up to the decision maker to decide how much they care about supply chain risk. And that's the parameter alpha that can be tuned appropriately as the decision makers want. So this this is a summary of what what I've talked about in the context of supply chain of the IoT. I believe supply chain is an emerging topic, particularly in the IoT, and it has become recently a new attack vector on top of other sort of attacks. But the analysis of supplier-induced risks is very complex because of the network scenarios. What I've presented today is one way to look at the problem, where we decompose this scenario into the supplier layer and the system layer, and we try to compose them together, and hopefully we can make decisions of suppliers that reduce the overall risk. But we really need some more sophisticated integrated techniques to analyze the risk and take some better informed decisions for supplier choices. So I guess that will be it from my side, and I'd be happy to take questions at this point.
Okay.
Yeah. Let us wait for the questions.
Okay. So Junaid, I actually have a couple for you, and just out of curiosity.
Mm-hmm.
So one of the things that the Internet of Things sort of encourages in a way is various parts of the ecosystem to share data.
Right.
Okay, so if I were to take a look at, let's say, the automotive sector, you have the OEMs, you have around 400 tier 1 suppliers, then tier 2 and tier 3. So if you look at them overall, they all sort of collect data, and so does the OEM on how various stuff actually performs. Right?
Right.
And so there are now techniques like homomorphic computing, things along those lines, actually allow you to probably probe that risk analysis a lot more deeply without revealing what I would say is competition-sensitive data. Okay?
Right.
So have you looked at any regimes like that where what you're looking at is actually supplemented by real data? Okay? And what would the impacts of those sharing regimes be?
Right. I think if we have common vulnerability disclosures, or if there is some central database, I think that is going to be have a positive impact in terms of the risk assessment. I'm not sure how it directly works with the framework that I've been working on.
Well, so let me think of a specific example. You have, let's say, Takata, which was a producer of airbags, or components for airbags. They have a dominant position in the industry. Okay? And so what you found is, in the end, everybody suffered, because you had to do recalls on cars by almost all the OEMs.
Right.
Okay?
Right.
And had they, in fact, shared data and caught that earlier,
right,
the pain would have been a hell of a lot lower, and the risk would have been a hell of a lot lower.
Right. I think it's a very tricky situation because there are so many parties involved, and there is no obligation for any party to share information.
Correct.
It is. I mean, you're right. It would have been helpful in all cases if there is vulnerability disclosures, or there's some clearinghouse where people come together and test collectively. But unfortunately, the way the industry works with proprietary stuff, oftentimes things have to be based on experience. So as you mentioned,
Well, yeah,
that's example. I think once this this has been discovered, then the trust level has reduced, right?
well. So let me think of two sort of examples. If you look at, let's say, it's a different industry, but I think it illustrates the point. If you look at something like the oil industry in the North Sea, they all share failure data on equipment.
Right.
They were induced to do that by having one horrific accident called Piper Alpha, okay, and came to the conclusion that the greater good was to actually share the data, okay? And it had a remarkable impact, I would say, both on safety and on the risk that they were carrying, okay? Okay, the counterexample is in the Gulf of Mexico, the operators couldn't figure out how to get together to do something similar, okay? Okay, but there are shining examples of this, and so the question is, you know, how do you actually promulgate that as a best practice in the industry?
Well, you know, these things are very subjective. Even though you have agreements of data sharing, there is no guarantee of the accuracy of information people provide you.
It's pretty good because it's audited actually under the agreement.
Okay, I think as I mentioned earlier in the overview of the framework, if there is common vulnerability disclosures, that is actually very helpful in determining trust or in establishing these trust values and reliability values that are useful for our framework. As I said, a lot of this work depends on how accurately we are able to characterize reliabilities and trusts of suppliers. And I think if there is this sort of information sharing and public auditing, I think it's going to increase trust levels by miles.
So there is something called ANX in the automotive business called the Automotive Exchange.
Right.
That does this at some level, essentially.
That's good to hear. I'll certainly follow up with this and see how these sort of things can also be integrated into theoretical frameworks and making decision making much better.
Yeah. Okay. I think we have some other questions that have come from other people. So I think, Bala, do you want to read?
Yeah. So from the same attendee which we had in the previous session with two questions, the same attendee whose name is Onur Vosturk asks a question. Is it meaningful to incorporate the purchasing costs of the components into the risk analysis you have presented so that the overall cost can be assessed?
Let me try to understand. So purchasing cost of the components is, so the cost of component is part of the budget constraint. So oftentimes when you have many choices, then it is limited by some constraints, and in this case you have limited budget. So if you want to incorporate the budget into the risk, I don't think that makes sense because they are kind of different quantities. There may be some reliable product, but it may be expensive, or vice versa. So they go hand in hand, but I think the place of the budget is the constraint, not
well,
the risk.
So let me ask a question. Again, if you look at the OEMs in the automotive business, usually you'll have what you call the just-in-time suppliers bringing the main assembly plant, okay? So the ability to switch people is fairly difficult, in fact, and impacts the cost significantly.
Right.
So I think you know, in a way, you sort of posed that question before, and then you can say is, how much emphasis will a OEM place on cost versus place on risk?
Absolutely. I think this is a better way to think about it. So oftentimes, risk may not be an objective because, I mean, it may be an afterthought. Companies often care about money and profits, so they may want to optimize their costs instead, and hopefully keeping their risks in a under some number, which may be regulated or something like that. That can certainly be done with what I'm talking about today. I think the framework allows us to do it, but it's just I haven't presented it in a way which is cost-centric. I think the focus has been on risk minimization, and to see whether it really works or not.
Okay.
So we have one more question from the attendee, a different, his name is Evandro. So his question is, what do you think about using blockchain to store device identities to build trust between IoT devices together with the network characteristics to reduce risk levels of having malicious IoT nodes?
Okay, so I think it is part of the risk. Again, device identities is important. Certainly, blockchains can be used, if you will, to have this transparency and maintaining accuracy of records. But when you talk about trust and risk, I think it goes much beyond just identity. As I said, there's going to be other things like vulnerabilities or some intentional life from some of the suppliers, like hidden backdoor channels and so on. So I think trust is not limited to just identity. It's part of it, and definitely blockchain, if you will, it can be used to solve a part of the problem, but not everything. I think the problem itself is very, very complex, and as I said, trust is beyond the scope of our work and our expertise. It is a much difficult topic.
So one more question, I think, going back to the previous topic. In the model that you have, there seems to be quite a bit of regard for what I would say is the ultimate ownership of the suppliers or sub-suppliers. Okay?
Right.
So if you were to actually look at the structure of the supply chain, let's say tier one, many of them, and I think you mentioned it, happened by acquisition. Okay?
Right.
Okay. And at that point, the structure of the supplier really matters, because many of them are still operated as very independent organizations.
Right.
So are you overstating the risk? Okay, when sort of, you know, without sort of a closer examination of who the actual owner is and what structure they use.
Right. I think it is an overestimate, certainly, because we are making a very generalized assumption of the risk being propagated just because you are affiliated with some supplier group. But that's the way we are able to think about it, because we do not know the details. And oftentimes it's not public.
Well, except for the following, okay. So if you look at a few standards that do exist, okay, how would you relate, for example, somebody? I'll say it's not somebody because I think it's a requirement for most of the OEMs. Things like ISO 9000,
right?
which actually give you quite a bit of insight into what a supplier does or doesn't do.
I think when we talk about malicious intent, these certifications may still go through, but if you think about backdoors or some hidden functionalities, they may never be apparent, and especially if you talk about microchips and these computers, they may have functionalities you're going to discover unless the supplier wants to use it himself or exploit it. So traditional quality assurance or testing may never reveal this. So the whole point is basically overstating the risk and trying to be aware of that, and hopefully avoiding possibilities that may lead to some unforeseen circumstances. But again, the thing is, it's up to the network designer. It's up to the entity deploying the devices, whether they care about supply chain or not.
Yeah.
In the case of U.S. government, they certainly do, but a lot of organizations may not care.
Yeah. So, but let me then ask the fun. So one aspect obviously is malicious intent, and you actually put a vulnerability or an exploit into the device. But the other is a lot of functionality that's put in, I would say for convenience, which can be exploited maliciously.
Right. Absolutely.
Okay. And so which one actually represents the bigger risk in this game?
I think the second one is more common.
Because I look at Stuxnet and I put it in the second category.
Yeah, right. So there's always good functionalities and features that attackers exploit, and it's going to be always the most common sort of risk. The malicious intent, I think, is a rare thing because companies do care about their future business. So it's a very risky thing to do. And unless you are...
well, if you're caught, you're dead, right?
Yeah, right. So unless the suppliers are totally, unknown and are there for just one or operating just for once, I think it is rare. But you never know. There are countries and governments involved, so there are certainly possibilities. But as you said, the second one is a more common and more serious one.
Yeah. So how do you evaluate that? Because that has a lot of unknowns with it.
I think there needs to be a vulnerability assessment expertise. There can be many ways. People can come together, share information, or do testing together to
yeah. So you black hat everything and try to figure out as much as possible. Yeah.
Right. I think the goal of our work is really at the top level decision making. Once you have this bigger picture, how can you make decisions?
Yeah. Yeah.
If you want to go into details, I think there's a lot of depth that we can go into.
Okay. Good. Anyway, really very good talk. I think we're at the top of the hour, but really want to thank you. Very well prepared, and I hope the rest of the folks appreciated it too. Okay.
Yeah, Junaid, I have one more query regarding a small query. So regarding risk mitigation, you mentioned many points about suppliers component. So the flow indicates a feed forward flow. You not indicate any feedback flow to mitigate risks. So normally, whenever we have a complex system, in case of any event, like since you're discussing supply management, sometimes whenever we estimate a model, and if it is a risk model, We need to have feedback somewhere in the middle
Close
or
the loop.
at the intermediate. Yeah, close the loop. Again, we need to reevaluate if we have a feed forwarding mechanism. So in that case, it will be very difficult to mitigate risks to full extent. To some extent, it might be possible. But in case if you want to have a robust system, we need to have a feedback, especially for a model like risk. So, but
right. I think this is a very good point. But the fact of the matter is, um, the system that we are looking at, all the entities involved are not under the control of one person. You see, there are different components that you deploy, but you do not have control of over the suppliers. So it does not really make sense if you talk about the traditional feedback, but I think certain elements of the feedback can, or certain inspirations can be drawn from feedback where you can change your decisions based on some things.
Yeah, but you also have, I would say, in the industry you just looked at, that larger and larger portions of design, and you actually bake in your suppliers at the time you design things. A lot of that is going to the tier ones.
Right.
And the consequence is that it is unlikely that a single organization, even within an OEM, has the choice of most of the suppliers involved.
Right. What I meant to say is the organization that is deploying a system or building a system may only have control over
a subcomponent of something.
Yeah, right. It may not be able to influence the risks flowing from the suppliers. So in that sense, I think traditional feedback may not be very applicable, but what I see is we can draw an idea from feedback theory to actually change our decisions based on how those decisions impact the risk.
Yeah. So the last part to this would be, none of this stuff is totally inanimate, and you do have, I would say, human factors involved. Okay. How do you play a role in this?
Yes, I think human factors add a lot of constraints. So there may be some risky or less trustworthy suppliers, but some human decisions are inclined towards that because of other factors. So I think as more factors get involved, I think we are going to have more constraints on how the overall system is going to look like from a supplier perspective. There may be agreements, there may be other different sort of constraints because of human factors, which I haven't looked into yet. I think this is an interesting expansion moving forward if this thing has to be implemented in reality.
Yeah.
So thank you for this comment. I think this certainly has to be put into place.
Yeah. Yeah. Good framework.
So,
good.
Yeah. So Adam, should I thank?
Yeah. Absolutely.
Yeah. So Junaid, thank you very much for your wonderful presentation and inspiring us in various aspects of understanding IoT security based on risks and resilience, and explaining various types of mathematical models based on security attacks and bots, and explaining something about risk mitigation. So we sincerely thank you on behalf of IoT WFIoT 2020, and next week we'll send you the presentation certificate. And in case if you receive any emails from the presenters, it'll be very interesting if you can help them in case they have some queries, in case you receive an emails.
Great.
So it will be very wonderful. So we thank you and your teacher also. And I wish you very good luck in your new job at the University of Michigan as a faculty member.
Mhm.
I wish you very good luck.
Thank you so
So,
much.
yeah, it's a new job. So after your PhD work, you should be enjoying the post at that university. So again, this IoT, WFIoT virtual events are still in progress. So
Mhm.
tutorial session concludes today. Today is the
Mhm.
last day of the tutorial week. So we have standard peak in 24th to 28th of August 2020. We welcome you and your team to attend this session of IoT. And in next month, mid of September, 14 to 18, we have vertical and topical sessions again as a part of a virtual event, which is based on industry and various academia persons. And in the last event of virtual week, we have Women in Engineering in the 23rd of September 2020. So we welcome you and your members to attend these sessions also and make it a success. Thank you very much. Good luck.
Thank you
So
again
I also,
for
yeah.
having me here.
So
Oh, and let me just say, for Friday afternoon, you had quite a few people from all over the world in on this. I think at the peak you had 36 attendees for the
yeah,
session, and a lot more registered. Okay?
Perfect.
Well, thank you very much.
Yeah, thank you
Thank you
so
very
much for inviting me and giving me an opportunity to speak at your forum. I really enjoyed it. And I'll be happy to answer any questions. Please, anyone who wants to get in touch, please feel free to send me an email. Thank you. Have a good day.
Yeah,
Great.
thank you
And
so much.
one final thank you from IEEE. Junaid, thank you very, very much. We really appreciate your time and effort that you put into this. It was wonderful. Bala and Adam, thank you for helping to coordinate it. It was a great week. But thank you, everyone. Have a great weekend and stay safe.
Thank you, Karen. Thank you, Adam.
Thank you, Bala. Bye-bye.
Thank you.
Bye-bye.
Thank you.
Thank you. Bye-bye.
Bye-bye. Have a good day. Have a good weekend.